Related to circular motion in that gravitational force helps us to look at the gravitational attraction of planets for each other. For instance, the sun attracting and causing the Earth to orbit, the moon orbiting around the Earth. We're looking at, in this particular section, universal gravitation and the laws that apply to it, the equation that ties to it. This is the law of universal gravitation. F sub g is gravitational force, just as we've always seen. Big G is the universal gravitational constant. Since it's a constant that would be given to you. It is a fairly small number, 6.673 times 10 to the negative 11, and the units are newtons meters squared over kilograms squared. And we can get the units by looking at the quantities that make up the rest of the equation. M stands for mass. So M1 is the mass of the first object. Many times, if we're looking at a planet and the sun, the moon and the Earth, an object on the Earth and the Earth, it is the source of gravitation. But we can also call it object 1. M2 is just going to be the mass of object 2. R could just as easily be written as D, or delta x. It is the distance between the two objects' centers of mass. Really what we need to be able to do is just be familiar with and be able to use this equation. So if we take a look at a problem where we have to find the gravitational force between a 500-gram mass and a 100-gram mass, and they're placed 1 meter apart. We can use this just as easily for small things as large things. The gravitational force we find between these two things is 3.315 times 10 to the negative 12 newtons. So pretty small, which is why they won't really attract each other. If we look at the gravitational force between the Earth and a human, we're going to see something a little bit closer to what we're normally accustomed to when we talk about Fg. In this case, what we find is we get a gravitational force between the Earth and this person of 688 newton. Now, just for comparison, if we were to find gravitational force the way that we've done it so far this year, which is just m times g, we'll take the person's mass of 70 kilograms times 9.81 newtons per kilogram, and what we find is we get 687 newtons. So this is an approximation of this, but for our purposes it works quite nicely. Now, if we look at the third one, we don't really have to do a whole lot of math. It's more of a work it through a thought problem. What happens to the gravitational force on an object when its distance from the center of the Earth is doubled? So instead of r, we go to 2r. So if I'm doubling the distance is in the denominator first of all, so increasing the distance is going to make Fg bigger or smaller. Hopefully you came up with the idea that Fg will be smaller. Secondly, because in the denominator r is squared, we're going to take the whole quantity 2r and square it. So Fg is going to be smaller. Not only is it going to be smaller, it's going to be 4 times smaller.